Hey guys, here's your video notes for gas stoichiometry, density, molar mass, partial pressure, all that fun stuff. I'm going to apologize right now because I did these notes at home and had to use a mouse, so my handwriting on this is bad. Please, please be kind. I'm going to try to go through this fairly quickly here. Um, looking at everything, very first thing, normal gas law kind of conversion stuff. So if a gas is at STP, then you can use these mole conversions right here. There's exactly 22.4 liters for every 1 mole of gas. So if you know the number of moles, multiply it by 22.4 to get to liters. If you know liters, divide by 22.4 to get back to moles. Um, if it's not at STP, then you have to go do the ideal gas law. So PV equals nRT. Just remember units matter. So this is atmospheres, this is liters, moles, and then degree Kelvin. This is R, which is always just plugged in. Okay, so from there, very first kind of practice problem for this whole thing. So if you have 1.75 liters of a gas at STP, well, divide by 22.4. That gets you 0.078. Um, Pretty self-explanatory. This one involves quicklime, which is produced through this whole process right here. So we know that we have 152 grams of calcium carbonate. So if we do some molar mass dealies here, we know that's 1.52 gram or moles. I mean, um, because it's 1-to-1 stoich. If we have 1.52 moles of calcium carbonate, that means we have 1.52 moles of carbon dioxide, and then from there, moles of carbon dioxide times 22.4 gives us 34.05 liters of carbon dioxide given off. Okay, so this one is obviously quite a bit heftier, so I would recommend that you guys maybe pause it and see if you can solve it, but I'll kind of clue you in on how to solve this whole problem here on the next slide. So I went and color-coded everything. Again, you're not really seeing my work here, but you're seeing the clues for how to do this. So all the red text gives you information on methane and oxygen, so you can find using ideal gas law, you can find moles of methane and moles of oxygen. From there, stoich to find moles of carbon dioxide. So this is a combustion reaction. So methane plus oxygen to make CO2 and water. So use stoich to find carbon dioxide. Ideal gas law to find volume of carbon dioxide. You need the green text up here to do that. So when you know moles, plug that in with this info to get to find liters in the ideal gas law, and there's your answer. So again, I would recommend that you guys try this problem out because it kind of puts all that stuff together, and you should get 2.53 liters. Yeah, so that was all the stoichy kind of stuff. So it's just ideal gas law or using STP information. Density of gases, here's the equation for that. So molar mass equals the density times R times T over P. If you notice, this is a very modified version of ideal gas law. So it's pretty much the same idea. We've substituted stuff in there so that now we're finding molar mass. Density in this problem is always going to be equal to grams divided by liters. So this is not grams per mole or grams per milliliter, like when we talk about density of other things. Grams per liter. R is the same value, temperature is the same unit, pressure is the same unit, molar mass is grams per mole. So plug and chug kind of problem, very straightforward. Up here you can see what it is for different gases. So 1 mole of O2, if it's 22.4 liters, well, then 32 grams. So you can use that to kind of figure out density and compare it. Okay, so practice problems using density. So We know the density of the gas, which is 1.5. Was the density of the gas was measured at 1.5 atms and 27 degrees Celsius, and it's found to be 1.95 grams per liter. So calculate the molar mass. So plug in density, plug in R, plug in K. Sorry, not K. Well, K is in Kelvin, so temperature. So 27 plus 273 to get Kelvin, and then divide by 1.5 atms. So this thing has a molar mass of 32.0 grams per mole. Well, going back, hey look, 32 grams for 1 mole. So it's O2. This is oxygen. Okay, so over here, Dalton's law of partial pressure. You guys probably saw this back in honors or regular chem. Pretty straightforward. If you know the partial pressures of various gases, you can add them up to get the total pressure of the container. So I'm sure you guys have done this a bunch. So pressure of gas 1 plus pressure of gas 2 plus pressure of gas 3 equals the total pressure of the system. I wouldn't be surprised if we did this back when we did gas equilibriums. We can also do mole fractions. So mole fractions is usually written as x to the sub whatever gas you're talking about. So gas A versus gas B versus gas C. If you know how many moles of gas A you have, you can divide it by the total moles of the entire system to get the fraction of how much, like the mole fraction of gas A. Do the same thing with B, do the same thing with C. So the reason why you can use mole fractions and why mole fractions are important is because you can use this modified version of Dalton's law. So mole fraction times total pressure will tell you the partial pressure of that gas. So if you know the mole fraction of that gas times the total pressure, you can find the partial pressure. So really, it's just depending on what the problem tells you. You don't necessarily know all of the partial pressures, but if you know what the mole ratios are, you can find it this way as well. And this text is just kind of describing that same thing. So here's an example of Dalton's law. So up here it gives a bunch of information. So it gives liters and temperatures and pressures of two gases, oxygen and helium. So you can use the ideal gas law to find the partial pressures of both those gases. So oxygen has a partial pressure of 2.4, helium is 9.3. So the total pressure of the system is the sum of these two gases, so 11.7. So again, because it's hard for me to write where I am right now, I didn't really show out all my work here, but it's fairly straightforward, and if you want to see it, it's good practice of ideal gas law. So values right here for helium, values right here for oxygen, and then you can find the total pressure of everything. This particular problem, now we have mole ratios. So it is asking us to find the mole fraction of O2 present in this whole system. So we know that the partial pressure of oxygen is 1.56, and we know the atmospheric pressure is 7, or we know the total atmospheric pressure is 743 torr. We don't know anything about other gases, so there's obviously other gases involved because we're talking about air pressure, but all we know is that we have a partial pressure of oxygen and the total pressure. So plug in total pressure, plug in the partial pressure of oxygen, we can solve for the mole fraction of oxygen, which in this case is 0.21. Also, going back really quick to you notice that this thing is unitless because it's moles divided by moles. So just because of the nature of mole fractions, you don't put a unit. Okay, so water displacement is another way to solve for stuff, and you guys will be doing a lab like this next week. There will be a video that goes with that, the lab instructions, that is totally worth it to watch, so please do watch that. But the general idea here is you do some reaction in this case, a test tube or another container, and you connect that entire thing by a tube system, and that goes up into this beaker or whatever that is upended into water. So before the reaction starts, this entire thing is full of water, and it's upside down in water. So as you produce gas, the gas is going to follow this tubing, and it will fill up this container, so that this right here is just that gas. Um, there's no atmospheric gas in here to deal with, so you're just collecting this particular gas. Couple things that are worth noting. Again, the whole idea is make sure that there's no air bubble in here to begin with, and because there is water here, water does have a slight vapor pressure. And the surface of water anywhere, you will find a level of water as a gas, so you'll find a level of water vapor, and it will depend on the vapor pressure at the time. So you need to know the vapor pressure off the water here, and you'll have to subtract that from this gas bubble here. That way you're removing the water. So you'll find the total pressure of this gas bubble, and then you need to subtract the partial pressure of water vapor to get the partial pressure of the gas that you're collecting to actually run any math. So again, you guys will do a lab like this. Do watch that video. Yes, I know it's just a do. So watch that video because it kind of walks you through this quite a bit more. But yeah, it's very important that due to water vapor, you need to correct for it. So you need to find you'll usually look up the partial pressure of water vapor at that particular temperature and correct for it. So here's an example right here of water displacement. So this is the solid. We're heating that solid up in this little container, getting it to decompose into these two things, collecting this O2 gas, and they want to know, based off of what we collected here, or based off of what we used here, calculate the partial pressure of O2 collected and the mass of KClO3 in the sample. So we'll have to find the partial pressure of O2 and then go backwards to figure out what mass of this we actually end up using. So color-coded walkthrough again. Using the green text, you can use Dalton's law of partial pressure to find O2. So we know the total pressure, and we know the partial pressure of the water is 21. So subtracting, we can find the partial pressure of oxygen. So little mental math, what is that, 733 torr. Using the ideal gas law, we can use that to find moles of oxygen. So that's 733 torr. Convert that to ATM because it's ideal gas law. Plug that in for pressure. You know volume because it's right here. You know temperature. You'll have to convert this to Kelvin. Plug and chug and find moles of oxygen. When we know moles of oxygen, well, we have this reaction here, so we can use Stoich. For every 3 moles of oxygen that were created, 2 moles of this guy had to have been used up. So you can do BCA table or dimensional analysis to find moles of KClO3. Once you know moles of KClO3, find grams. This is the final answer. So again, this is a good one for you guys to try out because it forces you to use this, this, and this, and put it all together to find a total answer. So anyways, I hope those notes worked. I'm sorry I didn't write out as much because, again, it was difficult and you could see my bad handwriting. Let us know if you guys have any questions, and know that you guys will be doing a lab with this soon. So make sure that you guys kind of get these skills down. See you later.